Welcome to the Combined Physics Paper 2 Waves revision. When we're labeling waves, we need to know the main features of it. Wavelength is the distance from one point on a wave, crest here, to the same point on the next wave. So it has to go exactly from one crest to the next crest. You could, of course, do it from one trough on a wave to the trough on the next wave, but it must go from one point on a wave to the same point the next wave, always measured in meters. The amplitude of a wave is the highest or lowest point it goes up or down to from the undisturbed position. So the amplitude is the up to the crest or down to the trough, again measured in meters. When we're talking about waves, we also need to think about the frequency of the waves, the number of waves that are being produced each second, and we also need to think about the time period, the time taken for one wave to be made. Once we've got some of those measurements of a wave, we can use the speed, frequency, wavelength calculation. V for velocity equals F times frequency multiplied by the Greek letter lambda, used here to stand for a wavelength. So the speed of the wave equals its frequency multiplied by its wavelength. Again, frequency has to be in hertz, wavelength must be in meters. We remember that with our very fatty lamb. V, F lambda, speed equals frequency, wavelength. Two types of wave, transverse and longitudinal waves. To make a transverse wave, just like every single wave, something oscillates and then energy is transferred. Now, in this example, the oscillations are perpendicular, right angles to the way the energy goes. With a longitudinal wave, though, it's the opposite. The oscillations are parallel to the direction that the energy actually is transferred. So with transverse wave, oscillations are perpendicular to the energy transfer. With a longitudinal wave, the oscillations are parallel to the energy transfer. Good example of transverse waves is water waves. So the water moves up and down, but the waves take the energy across the pond. Sound waves, good example of longitudinal waves. Your speakers move in and out, and the sound waves come out parallel to the way they're oscillating. Again, we mentioned frequency and period. Frequency is the number of waves per second. So if we got all these 1, 2, 3 complete waves in 1 second, we could say that wave has a frequency of 3 hertz, 3 waves a second. The time period is the amount of time it takes for just one wave. So to work that out, we need to use the equation that the time, or the period, equals 1 divided by the frequency, or time is 1 over f. Now you don't need to learn that equation, that's one that's given to you on the formula. If we want to make measurements of the wave speed, then we're going to need to measure those two things about a wave, its frequency and its wavelength. To measure the wavelength of a wave and the frequency of wave, we can use the bit of equipment called the ripple tank. You were shown this in lessons. We have a little tank which little ripples can be sent along, and we can use that then to have a look at those waves. We shine the light down on that so we can actually see the waves to make measurements. The wavelength is just measured using a ruler. You just measure from one wave to the next wave, crest to crest on one wave with your ruler to measure the wavelength. Now to help do that, you can use the strobe light, the very fast flashing light above the ripple tank, to make it look like the waves are frozen and not moving. To measure the frequency of the wave, then we count how many waves go past in 10 seconds and then divide by 10 to work out how many waves there are in 1 second. So count the number of waves that go past in 10 seconds and divide by 10. So we've got our wavelength for measuring crest to crest with a ruler, frequency by counting how many waves pass in 10 seconds and divide by 10. And then we can use the frequency, we can use the wavelength in the speed equals frequency times wavelength equation to work out the wave. Some of the best known waves, the waves we've learned most about in this topic, are the electromagnetic waves, which are on the electromagnetic spectrum. All those waves, all the way down from rotor waves, all the way through microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. We have to learn them in that order because those waves are going from long wavelength radio waves up to short wavelength gamma rays. They're going from low frequency radio waves all the way up to high frequency gamma rays. They're also carrying low energy, the radio waves, and high energy, the gamma. All electromagnetic waves have a couple of things in common. They're all transverse waves. They all transfer energy, just like all waves. They can travel through a vacuum. So it's different from things like water waves and sound waves, which need water or air to carry the energy through. And they all travel at the same speed, the speed of light. So all electromagnetic waves travel at the same speed. You then need to learn your uses and dangers of the electromagnetic spectrum. Everything from radio waves used for communication and TV signals, microwaves used for your mobile phone signals, infrared used for remote controls, visible light for seeing things, ultraviolet used in sunbeds, X-rays, medical uses like treating cancer and taking images of broken bones, and gamma rays used for treating cancer or sterilizing equipment in hospitals. In terms of the dangers, they get more dangerous as we move up. Microwave TV have very few dangers. We then focused on a couple of particular waves. Infrared was the first one that we looked at. Infrared radiation is carrying heat energy. Now, absolutely everything is emitting, taking in infrared radiation, and absorbing, giving out infrared radiation. You might think that just because something is very cold, it's not giving out any heat energy. It is, it's just hardly giving out any. We just say that the hotter the object, the more infrared radiation it emits. Now, all objects emit infrared radiation, like we were saying, but they all absorb infrared radiation as well. They take in infrared radiation. Turns out the best colors for absorbing and emitting are dark, dull, matte surfaces. The worst ones for absorbing and emitting are light, shiny surfaces. So if you want something to absorb infrared radiation quickly and heat up quickly, or you want it to emit infrared radiation and cool down quickly, then we use dark, matte colors. If we want something to warm up slowly, absorbing infrared radiation slowly, or cool down slowly, emitting infrared radiation slowly, then we use white, shiny colors. We proved that those different colors affected how we emitted infrared radiation using the bit of equipment called the Leslie cube, just that cube of copper with different color sides on it. So if you're asked for an experiment you can do to show that different colors affect how we emit infrared radiation, you can fill up the Leslie cube with hot water, and then you can use your infrared thermometer to figure out the temperature of each side. You'll find that the matte black side, because it's the best emitter, has the highest temperature, and the white and shiny silver sides will have the lowest temperature because they are the worst emitters of radiation. We then looked at the more dangerous electromagnetic waves. Ultraviolet, X-rays and gamma rays can all cause mutations and damage to our cells, which can lead to cancer. Now, because ultraviolet rays don't carry quite as much energy as X-rays and gamma rays, they can't penetrate through your skin so far, so the cancers and damage they cause are skin cancers and premature aging of your skin. X-rays and gamma rays can penetrate further into your body, so they can cause mutations inside, which could lead to cancer. Now, X-rays and gamma rays can, of course, be useful. We use them to take X-ray images of broken bones, or we use them to treat cancer inside someone's body. The X-rays can penetrate through the soft bits of your body, like skin and muscle, but they are absorbed by those dense, hard bits of your body, like bones. So they make an X-ray picture of your body where the X-rays have been absorbed by the dense bones. Gamma rays can penetrate through your body, and we can focus them on cancer cells inside your body and damage and kill those. How do we make X-rays and gamma rays if we need them? Well, X-rays can be made when the electrons in atoms drop through lots and lots and lots of levels towards the nucleus and emit a high energy electromagnetic waves. Remember, when electrons drop down towards the nucleus, they are giving out electromagnetic waves. They're losing energy as they fall down. If they make a big drop down, then they could give off a high frequency, short wavelength, high energy wave like an X-ray. If we want gamma rays, they normally come from the nucleus of an atom, a radioactive atom which is giving off gamma rays. All waves, when they meet materials, can do various different things. They could be absorbed by the material, which means soaking up and taking in the energy. They could be transmitted by the material, like light going through a window, where all the energy just passes straight through. They could be reflected by that material, where all the wave bounces off the new material. They could be refracted, where they pass through the material, but they change direction on the way through. A refraction experiment to look at how a ray of light changes direction going through a block of glass. When the light goes into a block of glass, it slows down. Waves will slow down when they go through something more dense. So the ray of light is traveling through the air, then it starts traveling through the glass, and it is more dense, so the light ray slows down. When it comes out of the block of glass on the other side, it goes back into the air, it speeds up again. And so you can see the ray of light changes direction when it slows down, changes direction when it speeds up. To remember which direction it bends, we use the tagaga mnemonic. We remember that the ray of light moves towards the normal when it goes from air into glass, and then it goes away from the normal when it goes from glass into air. So tag. Refraction can also be explained, rather than drawing a straight line for the ray of light or straight line for the waves, it can be explained thinking of the waves as a row of wave fronts, a bit like the waves coming across the ripple tank. If you use that idea, it's helpful to think that the edge of each wave hits the new material, and that's when it changes direction. That's when it slows down and changes direction. Like, you could think of it as water waves traveling along and then slowing down when they get to the shallow water near the beach. They're going to change direction. So you may be asked to draw the waves as a wave front rather than a straight line, and you just bend them as they go into the new material. The waves, the edge of the wave changes direction as it goes into the material. Also, higher tier, we're going to have a think about how radio waves are used in communication. To produce radio waves, we need an oscillation in a circuit. So there's my electrons oscillating a circuit. Oh, if I've got electrons going backwards and forwards, electric current changing direction, I've got alternating current. So alternating current is going to produce these radio waves. The radio waves can then be absorbed in other circuits. Now, if they're absorbed in another circuit, they can start those circuits oscillating. So I've now got an alternating current in this circuit where there wasn't one before. So alternating current in this circuit produces radio waves. Those radio waves are absorbed in another circuit, and that starts alternating current there. The important thing to remember is that the frequency is going to be the same in the first circuit and the second circuit. So if I'm alternating at 50 hertz here to make radio waves with a frequency of 50 hertz, then this circuit is going to start oscillating at 50 hertz. So I'm going to get alternating current at 50 hertz in this circuit as well. Good luck.